The question is, what is generalized Hooke's law? Let's first review where we are now. First, we talked about the stress-strain relationship under a uniaxial loading situation. In this type of loading, the stress is the normal stress and the strain is the normal strain. A typical stress-strain relationship for a ductile material is shown right here. Hooke's law addresses this initial linear elastic segment. Hooke's law says the relationship between the stress and the strain is sigma equals E times epsilon, where E is the Young's modulus. Similarly, if I take a specimen and apply a simple shear loading, applying basically a single shear stress component, tau, this is the typical shear stress versus shear strain relationship for a ductile material. Once again, focusing only on this linear elastic part, tau is related to gamma, where gamma is the engineering shear strain, by this equation. Tau equals G times gamma, where G is the shear modulus, right? In addition, we learned something about Poisson ratio. For example, if we take a cubical specimen like this and apply a strain in the x direction, epsilon x, there's going to be strains in the other two directions. The specimen is going to shrink in the other two directions y and z. The corresponding strains are related to epsilon x by these equations. Epsilon y equals minus nu times epsilon x. Epsilon z equals minus nu times epsilon x, where nu is the Poisson ratio, right? Alright, so that's where we are now, right? In the uniaxial loading situation, the normal stress is changing only in one direction, which is the axial direction in this particular case. In the simple shear loading, only one of the three shear stress component is changing. We know a stress tensor has at least 6 independent stress components, right? 3 normal stress components and 3 shear stress components, right? So that begs the question of what if all 6 of them are changing? How do we calculate the corresponding strains? So this is where the generalized Hooke's law comes into the picture. Now let's talk about the generalized Hooke's law. With respect to a rectangular Cartesian coordinate system x, y, z, these are the 6 independent components for a stress tensor, right? Sigma x, sigma y, sigma z, the 3 normal stress components, tau xy, tau xz, and tau yz, the 3 shear stress components. The corresponding strain components are these. Epsilon x, epsilon y, and epsilon z are the 3 normal strain components. Gamma xy, gamma xz, and gamma yz are the 3 engineering shear strain components. The generalized Hooke's law can be written in a couple of different ways, and this is one particular form. There are a total of 6 relationships. 3 of them relate the normal strains to the corresponding normal stresses, and 3 of them relate the shear stresses to the shear strains. Let's look at the first of the 3 normal stress-strain relationships. Epsilon x equals 1 over E times sigma x minus nu times sigma y plus sigma z. We note that all 3 of the normal stresses, sigma x, sigma y, and sigma z, affect the value of epsilon x. If you're trying to understand the pattern here, the first stress component right here goes with the strain that we are seeking. So this is going to be sigma x because this is epsilon x, right? And you put the other 2 normal stress components here and multiply that by the Poisson ratio. Now if you look at the other 2 relationships, you'll see a similar pattern. Epsilon y here, and therefore you put sigma y here. Epsilon z here, and therefore you put sigma z here, right? And then the remaining 2 stress components will go within the parenthesis multiplying the Poisson ratio. Now for the shear stresses and strains, you see completely uncoupled relations. Gamma xy is completely related to tau xy. It is not influenced by tau xz or tau yz, right? So each of the 3 shear stress components are related only to the corresponding shear strain components. So I made some comments here. Note number 1, normal stresses don't produce shear strains and shear stresses don't produce normal strain. And you see that clearly from these relationships, right? We don't have any normal stresses here. We don't have any shear stresses here, right? Note number 2, due to Poisson ratio effect, each normal strain component depends on the changes in all normal stress components. So this is what we discussed a minute ago. Epsilon x depends on all 3 of the stress components, sigma x, sigma y, and sigma z, and so on. If you look at the first relation, if Poisson ratio is 0, this term would have been 0, right? And therefore epsilon x would be simply related to sigma x. And so that is why we call this the Poisson ratio effect. Note number 3, the shear stress strain relations are completely uncoupled. Tau xy is related only to gamma xy, not to gamma xz or gamma yz, and so on. Note number 4, a qualifier. The above relations apply only to isotropic material. These are materials for which properties are directionally independent. If you do have anisotropic materials, there's going to be Young's modulus in each of the 3 directions. There's going to be E1, E2, E3, and so on. The same thing applies for Poisson ratio and the shear modulus. So the overall relations are going to be a lot more complicated. There's going to be a lot more material parameters involved in the relations. Finally, let's convince ourselves that the simplified relations we discussed earlier are actually embedded within these generalized relations. Let's consider the special case of a uniaxial loading where a one-dimensional rod is subjected to a load P only in the x direction. Sigma x is then given by the load divided by the cross-sectional area of the rod, P over A. Sigma y is 0, sigma z is 0. From equation number 1, epsilon x is 1 over E times sigma x minus nu times sigma y plus sigma z, but sigma y is 0, sigma z is 0, right? So we get sigma x equals E times epsilon x. Now from equation number 2, epsilon y is 1 over E times 0 minus nu times 0 plus sigma x, because we know sigma y is 0, sigma z is 0, right? And that leads to this relationship where we know sigma x over E is epsilon x, and therefore this works out to be minus nu times epsilon x. From equation number 3, we get this relationship. Epsilon z is minus nu times epsilon x. So now we see the 3 relations relevant to the uniaxial loading are recovered from these 3 generalized relations.